Okay, let's get started, everybody. So, we're continuing on. We're on to 3D.1, and here we're going to talk about points of inflection. So, what is a point of inflection? It's a point on the graph on a function where it changes shape. Okay? So what I would point out about this function here, this is some cubic function, is that it is concave down over this interval, and the point of inflection is the place on the graph where it changes to be concave up. Okay? Concave down, concave up. So that's a point of inflection. And yesterday we learned about stationary points of inflection. We learned about stationary points. These are points on the graph where the slope is horizontal, and we're familiar with maximums and minimums. But today we're going to really point out what is a stationary point of inflection. Well, it's a point of inflection, so it changes from concave up to concave down. It's a point of inflection where the slope is horizontal. So both of these are what we call stationary because the slope is stationary at that point. And this is what we call a non-stationary. Okay, so we have stationary POIs and we have non-stationary POIs. All right, and both of those are highlighted in our notes book here. Now, a point of inflection will occur when the second derivative equals 0 and the sign diagram changes sign on the second derivative. So that's what we're going to check for. We're going to start with this function, and we're going to go through and we're going to list all of the properties from it using a manual calculus argument, okay? And then we'll look at the graph to observe those things on the graph. So we're going to do everything we've done so far. What's so good about 3D.1 is that we recap when is it increasing and decreasing, when do the turning points occur, and when do points of inflection occur. We're going to recap all of those things. So if we want to find turning points and when it increases and decreases, we're going to find the first derivative, 4x to the 3. And we're going to draw its sign diagram. So if I want to draw a sign diagram of this function, I'm going to make it equal to 0, and I'm going to factorize it. I'm going to go, what's the highest common factor? I can see x squared here and x squared here, but also 4 is a factor of both of them. So I'm going to pull 4x squared out the front, and that'll leave me with x take 3 in the brackets. All right, remember, you've factorized it properly. If you expand it, you get what you had above. Okay, and then we'll just apply the null factor law. So either 4x squared is 0, or x take 3 is 0. This gives us x is 3, this gives us x is 0. All right, and so if we're going to draw a sign diagram of the first derivative, we have roots at 0 and 3. Now, I know as a maths teacher, it's a cubic equation, okay, and it has a positive a value, so it has this shape, which means it's going to come up, touch, and then cross. So it's going to be negative, negative, positive. Okay, so let's answer what we know about increasing and decreasing. So what we would say about this function is it's decreasing for x is less than 0, x is great, and then 0 less than x less than 3. Okay, so we have negative slope. Remember, this sign diagram tells us about the original function. We're decreasing for values less than 0 and for values between 0 and 3. All right, and then we'd be increasing for values larger than 3. Okay, so that's what we did in exercise 3b. Now we'll reflect, what did we do in exercise 3c? All right, we looked at stationary points. Now these are the places on the function where the slope is horizontal. Let's talk about this one first. We're very familiar with that. It's decreasing and then increasing. That means we have a local minimum. So we have a local minimum at x is 3. All right, and we'll just leave the y value for now. We can calculate it by plugging it in here, but we'll just leave it for now and fill it in a moment. So we have x is 3, some y value. And like when I'm doing a test, right, even when I'm writing solutions, and I'm going through and I'm answering these things, if something's going to take a little bit to process, I'll just leave it blank, and then when I'm going to graph it later and check everything, and I'll just put the number in there then. Okay, so I don't even try calculate it myself. I'm just going straight to the calculator, make sure we don't make an error. Okay, then let's flick back to 3C in our notes book. And so on page 32, and I'm looking at the sign diagram, and so we've got our stationary points box here. Look at the one on the far right. That's what we have, isn't it? We have negative and negative about some root, about the root A. And so what is this? This is a stationary point of inflection at x is 0. All right, so we can write that there. Stationary point of inflection at x is 0. And I know the y value here, like that's very easy to evaluate. When x is 0, the y value is 5. So we can put that one in. Okay, flip back over. So all we've done so far is recollect everything we've done in 3B, 3C. We did increasing, decreasing, we've done stationary points. Okay, now what we're going to do is find the second derivative. Okay, so this is my first derivative. All right, so now if I'm going to differentiate that again, all I'm doing is differentiating this function here. So that's going to give me 12x squared, take 24x. All right, now same deal, like we can just use our calculator to get these. Okay, so I can graph this function, and then I can tell my calculator, show me the graph of the derivative. And you'll notice as well, we've done option calc d on dx. There is d squared on dx squared. So you can just graph the second derivative as well. So we can get our sign diagrams straight from our calculator. Nonetheless, let's make the manual argument. So we need to find the roots. We'll factorize 12x. And then apply the null factor law. Okay, now, I don't expect you to know the cubics, but I probably would expect you to know the quadratics, okay? This is a quadratic function. It has a positive a value, which means it's going to open upwards, which means it's going to be above, below, above. It has this shape, all right? And always label our sign diagrams. This is the sign diagram of the second derivative. Okay, so this tells us then that we have 2 points of inflection. So a point of inflection will occur when the sign diagram of the second derivative changes sign. Okay, so this is a point of inflection because it changes from positive to negative, and this is a point of inflection because it changes from negative to positive. Now, we already know this is a point of inflection, because we've listed it here. We have a stationary point of inflection when x is 0. We've already discussed this one. I suppose this sign diagram of the second derivative is just revealing that characteristic to us, that it is a point of inflection. But it does tell us something new, that there's a point of inflection here, okay? So we have a point of inflection at x is 2. And then we've got to work out, is it stationary or is it non-stationary? Now the answer is it's not stationary. And it's not stationary because if it's a stationary point of inflection, it's going to appear here. Okay? Stationary points of inflection will occur in the first derivative. There's no stationary point of inflection at x is 2, which means it has to be a non-stationary point of inflection. Non-stationary point of inflection at x is 2. Okay, let's bring up the graph and then let's observe all of these properties of this original function. So if you can go into graph mode, graph the original function. I'm going to bring it up on Vivi here, PRC loading space 6, and we're join room. Alright, now I'll graph the same function that we've got here. It is x to the 4, and then take 4x to the 3, and then plus 5. Good luck. Cheers. Alright, and I'll just set my view window to standard. We might need to zoom out a bit. We'll have a look and see. Oh, that's not standard. View window, standard. Alright, so I can see most of it. I can't see that minimum y point, so I'm just going to make my y min a bit larger. We can see there's some minimum point there, so I might just double that or even triple it. Let's go to minus 30. Okay, there we go. We've got a nice view of the graph now. Alright, so let's talk about the features of this graph. And I'll draw it here so I can point to everything that's occurring. So, we have, it's going like this, comes down, it's horizontal there, and then it comes down, and then it changes shape here and goes like that. Alright, so I'll point out a few key features. We have when x is 2, maybe I'll just trace it for now, so I can get that y value correct. Cool. And then we have this point here. Alright, so let's just talk about all of these features that we've observed. Firstly, let's talk about increasing and decreasing on the function. We can see as you're walking along, you'd be decreasing. You're decreasing until you get to 0. Alright, horizontal at that point. Then it's decreasing again until we get to, so I might put some numbers on here, until we get to 3. Okay? When it gets to 3, you start increasing again. So we've discovered that just from our calculus argument. We can observe that on the graph by g-solving those points. We can see we have a local minimum at x is 3. Alright, and the y value, we can g-solve the minimum, or I'm in trace mode, I can just press the number 3, and I can't read that. I need to make it go down a little bit. G-solve that min. 22. Okay, so 3 and minus 22. Alright, so we can fill that in. And the other thing we can observe is a stationary point of inflection. Alright, so we can see concave up. It's opening upwards. The parabola is opening upwards. It's like a bowl pointing upwards over that interval. And then here is the point of inflection. That's where it changes shape. It's now pointing down, okay, over this interval. It's a bowl that's opening down, okay? That's our stationary point of inflection. So we can observe both of those features on the graph and when it's increasing and decreasing. Okay, then we found the second derivative. Here it is, and we already anticipated that point of inflection. All right, from the first derivative, and so now we've got this new one at x is 2. All right, here it is here, and you can see concave down over that interval, and here it changes concave up over this interval. All right, so not only do we say that there's a point of inflection occurring, but we're going to answer where is it concave down and where is it concave up. All right, so we have a point of inflection when x is 2. Let's get that value. Trace x is 2. I think we had minus 11. Okay, good. So we've found the points of inflection, but now we're going to comment about the shape. Okay, so concave up for values of x less than 0. All right, we can see that from here. When the second derivative sign diagram is positive, concave up. All right, let's just go straight from the sign diagram. Concave up for x is less than 0 and x is greater than 2. Look at that, concave up there, concave up there. Concave down for x, 0 is less than x is less than 2. Okay, let's observe that. Concave up over this interval for x is less than 0. Concave down from 0 to 2. I'll put that coordinate there, 2 and minus 11. Concave down and then concave up. So we can observe all of those features on the graph. Now you can G-solve maximums and minimums, but unfortunately you can't G-solve points of inflection. You do need to perform a little bit of calculus there from the sign diagrams. Okay, so I've made a mathematical argument. Let's look at how we can use our calculator to support us. Again, we're familiar with drawing the graph of the first derivative. So if I graph that, okay, I can G-solve those roots, 0 and 3, 0 and 3, and you can see below, below, above. Okay, that can tell you when it's increasing and decreasing. All right, so we're familiar with that. That's what we've been doing in the past exercise. But now let's go to y3, and again, we're going to press Option, Calc, d squared on dx squared. That's second derivative. I want to look at the graph of the second derivative. Okay, and I'm always saying this, just look at one graph at a time. If you have multiple graphs there, the calculator sort of freaks out a bit. It's slower, and you know, when you're trying to solve roots and stuff, it always makes you choose which function you want to know the roots for. Just select one function at a time. And so there you can see the roots being 0 and 2 of our quadratic, and above, below, above. So I make the mathematical argument, you can refer straight to your calculator. Just like the previous exercise, the minimum thing you're required to do, show the first derivative, draw its sign diagram, okay? And then make comments about it from there. So let's pause there. We're going to open the textbook and we won't just leap straight into the exercise. This is an enormous exercise, right? And we're just going to be deliberate about what order we go about it. So let's do question 1 together, and then we'll get you guys to have a go at question 2 and 3. So I want to draw question 1 up here because this is a good thing for us to go through together. So we have this graph here. I'll try and draw it. It's a cubic of some variety. And we have points A, B, C, D, and E. A, B, C, D, E. And then we've got a table of points A, B, C, D. And all we're doing in here is filling in whether it's positive, negative, or 0. Okay. F of x is the y value. All right. So at point A is the y value positive, negative, or 0. The y value here is positive. So we're just going to draw a positive there. All right, I think what I might do, rather than copying it down with me, let's just explain it quickly and then you guys can have a go at answering it. So, because it might take people a while to draw the table and stuff, and it doesn't take long to explain. So just have a look up here. All right, so point A has a positive y value, point B has a negative y value, point C has a positive y value, D is positive, and E has a y value of 0, okay? F of x is just the y value, and we're saying whether those points are positive or negative. F dash of x is the slope. So now we're asked, at that point, is the slope positive, negative, or 0? At this point, the slope is negative. You would be walking downhill at this point. We have negative slope. How about at point B? It's not positive, it's not negative, it's horizontal. The slope is 0 at point B. At point C, the slope is positive. At point D, you're not increasing, you're not decreasing, the slope is 0. And at point E, the slope is negative. Okay, is that clear? Yep, just talking about how whether you're increasing or decreasing at that point. That's what the first derivative tells you. Okay, Now the second derivative. This is where what we've learned this lesson. Okay. The question we're asked is it concave up or concave down at that point? Okay. If it's concave up, it's positive. If it's concave down, it's negative. And if it's a point of inflection, it's a root. It's 0. All right. So we can see point A, concave up. All right. It's concave up until we get to here. That's where the point of inflection occurs. So point A and point B are both concave up. Point C is the point of inflection. That's where it changes shape. That's going to be the root on the second derivative. So that is 0. All right. And then we can see it's concave down. That has a concave down shape over this interval. All right. So that's how we do question 1. Okay. Let's get you guys to have a go at question 2 and 3. Yeah, that's what we'll do today. Okay, so I am going to go over a bit here, guys, because we're going to go over question 2 here, and then we're going to flip back and do the stationary points conjecture that we missed out on yesterday. But the stationary points conjecture is actually not too bad. It's a good one for us to prove, and hopefully that makes us feel a bit confident with the conjecture process. So here we have the function x squared e to the x, and we're asked for part A, discuss the behaviour of the graph. Discuss as x approaches infinity, positive and negative infinity. What happens to y? What happens to the y value as x gets really large? What happens to the y value as x gets really negative? So this is all it means. It means as x gets large, what's going on with the y value? What's the y value approaching? Now we've got 2 ways of doing this, okay? The first way is to just look at the graph. All right, so let's do that, and then I'll make the mathematical argument for you. Okay, so I think my V window is the same as it was before, but basically you can see as x is, I'll sketch it here, and there's a little bump somewhere here, I think. As x is going to infinity, as x gets larger, y just gets way larger. Okay, so all we'll say as x approaches positive infinity, y also approaches positive infinity. And then hopefully as well we can see what's going on here, an asymptote as x approaches negative infinity. As you trace along it in the negative direction, y is getting closer and closer and closer to 0. So that's the answer to part A. Now, not necessary, but as a technicality, we can also say that it approaches 0 from the positive direction, okay? Because it's approaching 0 from above the x-axis, okay? So it's never going to reach 0, it's always going to be slightly positive, but it's pretty much 0 because it's next to nothing. Now, how would you argue that mathematically? So all you do is you think, okay, what's a really big number? 100's pretty big, okay? So if I put in 100, all right, what we're going to have, if I go when x is 100, y is going to equal 100 squared times e to the power of 100. And so you can just see this is an enormous number, right? As x gets large, y is getting super large. This is going to, 100 squared is 10,000. And then e to the power of 100, well that means 2.72 times 2.72 times 2.72 times 100 times. So it's just an enormous number, all right? So as x gets large, y gets super large. As x approaches infinity, y approaches super infinity. All right. What about the opposite case? Okay. What about when we go in the other direction? If we're making a mathematical argument, if x is negative 100, then y would be negative 100 squared times e to the power of negative 100. Now, negative 100 squared is still positive 10,000. It's still a positive component. But then we have 10,000 multiplied by 1 on e to the power of 100. And now I just want to focus on this part. 1 on e to the power of 100, that means 1 divided by 2.72 times 2.72 times 2.72, like this super large number, okay? I have 1 divided by an enormous number. If you have 1 cake divided by, if we have 1 cake and we divide it by everyone on the planet, everyone's going to get a really, really tiny amount, almost 0, right? Everyone's going to get 0 crumbs. So this component, okay, this part is approaching 0, And so 10,000 times 0 is 0. All right? And so this whole thing, as x gets negative, gets super negative, it's getting closer and closer to 0. Now that's how we can argue it mathematically, but we don't need to do that, we can just look at the graph. I don't want to spend too long on that, but I'm happy to explain it to you in more detail if you would like. Let's move on to the second part then. We've got find the first derivative and draw its sign diagram. So if I'm going to differentiate this, I need to use the product rule. So the first derivative then will be u dash v plus u v dash. And if I'm going to draw its sign diagram, I want to know its roots. So that means I would make it equal to 0. And if I'm going to try and solve these roots, I'm going to factorize it. I've got x e to the x is common. And then apply the null factor law. All right, and then to get when it's positive and negative, we'll just graph the second derivative on our calculator. And if I g-solve those roots, and you can't quite see, is it above, is it below? So you can zoom in on it, or you can just trace along it, right? So if I trace along it, so the root is at x is minus 2. Oh, so I've drawn those around the wrong way, sorry about that. Minus 2 comes before 0. So the root is at minus 2, and then you can see if I go to the left of minus 2, my y value is positive. So we have positive, negative, positive. Okay, find f dash of x and draw its sign diagram. That's part B. Hence state intervals when it's increasing and decreasing. Well, it's increasing when the first derivative is positive. So we'll have x is less than minus 2 and x is greater than 0, and decreasing between them. Oops. And you'd be able to observe that from the original function. If you zoom in on it, you can see increasing, decreasing, increasing. That's what we get from the first derivative. Okay. Hence state coordinates of any stationary points. Well, we have a local max here, increasing then decreasing. And a local min at 0. And when x is 0, the y value is also 0. And when x is minus 2, we could g-solve it, but if we want it exactly, it would be minus 2 squared times e to the minus 2. What's that? That's going to be 4e to the minus 2. It's absolutely fine to leave it like that. Another way to write it, 4 on e squared, that's the y value. Okay? Any of those is fine. So we have a local max there and a local min there. They're the stationary points. All right? Stationary points occurring when the first derivative is 0. All clear with that? All right, on to the next page then. We have find f dash dash of x and draw its sign diagram. So, in order to find f dash dash of x, this part here, 2x e to the x plus x squared e to the x, this is our first derivative. So we've already got that from here. That's our first derivative. So if we want to find the second derivative, we're going to differentiate this equation. Now, excuse me, that should be a power. We already know what the derivative of this part is because we've done it here. If you differentiate that, this is what you obtain. So we don't need to differentiate that part again. We know what that goes to. We're just going to focus on this part of it. And we're going to use the product rule, u times v. So u is 2x, u dash will be 2, v is e to the x, v dash is e to the x. So the second derivative then, u dash v plus u v dash. Okay, so all I've done there though is differentiate this part. Okay, so I've performed the second derivative of that part. However, we're still required to put right here for the whole second derivative, what does this part go to as well? And because we've already differentiated that part over here, I'm just going to copy it. When you differentiate x squared e to the x, you get 2x e to the x plus x squared e to the x. All right. Now we've got like terms here. They have the same base. They're both x e to the x. So we can add them together. So that's going to be just 2 e to the x. Here we'll have 4 lots of x e to the x. And then we have x squared e to the x. All right, so that's what the second derivative is. Now we want to find when it equals 0, because we want to draw its sign diagram. And we're going to find these roots exactly for now, all right? So if I'm going to try and solve something like this, I'm going to factorize e to the x. That's the only thing that's common to all of those 3 terms, is e to the x, right? And so we'd be left with 2 plus 4x plus x squared, and this is a quadratic. So if we're trying to find when it equals 0, well, the e to the x term does not equal 0, so then we're only interested in this quadratic. Now from here, there's lots of processes that we could use, all right? So you can try and factorize it. This one won't have rational roots. We can use quadratic formula, okay? I like quadratic formula because it's foolproof. You don't even have to think about it. You just plug the numbers into the algorithm and it will dish out the solution. We can also use our calculator though. So let's show you how we can use our calculator to solve polynomials again. So we'll go menu, equation, down the bottom. And you notice there we've got simultaneous equations, polynomials, or we've got a solver. We're going to go into polynomial because a quadratic is a type of polynomial. It has a degree of 2. And we're just going to type in the coefficients of a, b, and c. A is our x squared term, so we're going to have 1, we're going to have 4, and we're going to have 2. All right, so you can see that these are irrational roots. If I apply quadratic formula, this is what I'm going to end up with. So it's listing it as 0.585, but it's also telling me what it is as a surd, which is minus 2 plus root 2. So minus 0.585. So minus 2 plus root 2, and minus 3.414, minus 2 take root 2. 3.414. All right. So those are the 2 roots on this sign diagram. So if we're going to draw the sign diagram of the second derivative, so here we've got sort of 2 options. In the test, if it says exact roots, if it says the exact roots, then we would use this form because this is the exact answer. I'm just going to use the decimal notation because it hasn't specified for us. So minus 3 comes before minus 0.5. Okay. And then we want to know when is it positive and when is it negative. So we'll go back to our graph mode. And we'll graph the second derivative. And G-solve those roots. And they're going to be the same as the values we got before, the minus 0.585 and so forth. I'm going to bar it. There, so there's the minus 3.414. And if I trace along it, okay, so if I went into minus 4, you know, that's going to be to the left of it. You can see the y value is positive. So it's going positive, negative, positive. Okay, so that means we have a point of inflection here and a point of inflection here. And they're both non-stationary points of inflection, because if we have a stationary point of inflection, we know it's going to pop up on the first derivative. Okay, hence find the nature and coordinates of any points of inflection. So, we have non-stationary points of inflection at. And this is where you can answer in exact notation or as the decimal. Either's fine. So the x value minus 2 take root 2, and then that corresponding y value, and the x value minus 2 plus root 2, and the corresponding y value. Now to get that y value, we get that from the original function, not from the second derivative, and so that's why there's a bit of hopping around on the graph here, isn't there? So we're going to exit out, we're going to select the original function, and I want to know the y value when x is minus 3.414, that's this one, or minus 2 take root 2. So I can type that in, minus 2 take root 2, and it tells me the y value 0.383. And then minus 2 plus root 2. And it's going to tell me that y value 0.191. Okay, so we have non-stationary points of inflection there. Okay, and lastly, state intervals where the original function is concave up and concave down. And here, all we're doing is referring to our second derivative sign diagram. We can see concave up for x is less than minus 3.414 and greater than 0.585. Okay, and concave down in between that interval. Alright, so here we've recapped everything we've done, haven't we? We're performing differential calculus, product rule, factorising, finding roots, drawing sign diagrams, we're looking at the graph, we're stating when's it increasing and decreasing, when are there stationary points occurring, and then we've even gone ahead and found the points of inflection and when it has that shape. Now I might just talk about that graph. So this is the original graph. I'm just going to change my V window a little bit so I can really point out those features to you. So I just want to change my Y. I'm just going to change that to just zoom in on it a little bit. Okay, so now it's super exaggerated, right? So here's what the shape looks like. It looks like this. Okay, so we can see the local min and the local max. We found both of those. We can see increasing, decreasing, increasing. And we can see the points of inflection, okay? Here and here, all right? Concave up, all right? So a bowl opening upwards, concave down, concave up. So we can see all those features on the graph. All right, we are going to absolutely annihilate this conjecture problem now. So we have to do it because we're just running out of time, I think. What I'd probably like to do is we've only got 8 minutes, so I'm going to go through it and I'll just get you guys to watch. You can write down if you want to, if you feel comfortable doing so. But conjecture example 3 on page 34. This is the one we're going to go through for a stationary point.